This is part 2 of preparing samples for microscopy. We're going to talk about fixation and frozen tissues, fresh tissues. There's a lot that goes into this. One of the things you want to do is to consider your options, what you're going to do with the tissue in addition to microscopy. Are you going to do any biochemical assays or genomics? Are you going to store the samples long term? And do you know the best practices for long-term storage? If you're going to do necropsies of tissue, then you want to plan to keep your postmortem times as short as possible. And you want to have everything ready. I have seen too many people that use cutting tools in a way that creates crush or cutting artifacts. This is from my own experience in electron microscopy, which is even less forgiving than optical microscopy. You want to use a really sharp blade and to just use a gentle sawing motion to avoid crush artifacts. If you're doing chemical fixation, do you need to perfuse this sample? For example, larger organs, perfusion fixation gets it into the tissue using the circulatory system. But it's not easy to do, and it can use up a lot more fixative. And if you apply too much pressure, you can create other artifacts. But for things like lung and liver, big pieces of tissue, you really want to consider that. For small pieces of tissue, or if you're working with invertebrates, immersion fixation works very well. So work through what needs to happen so things are efficient. Have a second set of hands can speed up the process. Someone does the necropsy, someone does the processing, and a third person keeping records is very handy. Some labs prefer to cut large organs like brain, for example, into thicker sections using a vibratome, 200 to 300 microns in thickness. Then the sections can be chemically fixed or snap frozen or used fresh if needed. And vibratomes can be used on both fresh and fixed tissue. If you're using fresh tissue, you typically want to do it at low temperatures with a cold buffer to slow autolysis. You really want to plan your workflow so that you have the shortest amount of autolytic time. And small samples may be so small that they need to be in low melting point agarose to give them something surrounding them to enable them to be sectioned. And what's your planned use for the frozen tissue? What you freeze in can affect your biochemical analysis. For those who are doing frozen sections for microscopy, often freezing using OCT compound makes for better sectioning, but it's not as good if you're doing chemistry or genomics. And you have some limits on how thick you can cut things with that are frozen sections. Frozen sections can be better for certain types of antibody staining, particularly if the antibody doesn't work well against cross-linked or fixed tissue. And the other side of that coin is that frozen tissue morphology is typically not as good as chemically fixed tissue. The problem with freezing is ice crystals. If you freeze too slowly, you encourage the growth of big spears of ice crystals, which will punch holes in tissues. I have seen tissue that looks like Swiss cheese because people froze too slowly. You want to do something that freezes the tissue and creates amorphous ice that doesn't really have a structure, and it stops the autolysis a lot faster. In our experience, with light microscopy, liquid nitrogen cooled propane or isopentane tends to work the best, with dry ice ethanol being sort of a distant second. If you happen to choose to use the dry ice ethanol method, make sure to keep the ethanol from mixing with the OCT compound. It doesn't work as well when you contaminate the OCT with the ethanol. And there's a skill involved in doing this kind of freezing to get the best results, and it's good to practice so that you get it right. Doing it the first time with something critical is an invitation to frustration. Smaller samples tend to freeze more uniformly. Larger samples tend to have thermal gradients and may freeze poorly in the center. And there are techniques for electron microscopy for rapid freezing, but many of them require specialized equipment. Solvents like methanol or acetone, cold methanol or acetone, are sometimes used for frozen tissue sections on slides, sometimes for cells grown on cover slips. And this stops further autolysis, and it quickly dehydrates the tissue and also removes some lipids, which makes the interior of the cells more accessible. Samples can be stored in a freezer, stained with either colored stains or immunostaining, but the long-term exposure can be problematic because the surface is exposed to oxygen. And you wouldn't want to take these in and out of the freezer any more than absolutely necessary, because condensation will cause issues as well. You've just dried them out. Now you're adding water back in because of condensation. This does allow antibodies that don't work well on cross-linked fixative type tissues, but it has some downsides as well. Cross-linking fixatives are often done at room temperature because lower temperatures slow the penetration of the fixative and the actual reaction that causes the cross-linking. Formaldehyde, typically at around 4% or less, it is primarily for optical microscopy. Immunostaining is not usually a problem if you know that the antibody is known to work on fixed tissue. And they will usually tell you on the label or in the document that comes with it. Glutaraldehyde is primarily used for electron microscopy, and it's challenging to immunostain tissues fixed with glutaraldehyde because it's a very strong cross-linking fixative. Both of these are known carcinogens, so handle them with care. And the way our aldehyde fixatives work is through the cross-linking of sulfhydryl groups on the amino acids in the proteins. This doesn't preserve lipids or polysaccharides as well. Now, just to help you understand how to work with these, formaldehyde is a very confusing nomenclature, and it's based on historical reasons. It's been used for at least 100 years. Paraformaldehyde is a white powder, so it's a dry ingredient. And getting it into solution requires heat and some sodium hydroxide to get it to finally go into solution. You should always do this in a chemical fume hood. Trust me, I got a nose full of this when I was first starting out. You do not want to get this anywhere near your face. This happens to be the freshest way to make formaldehyde with initially no methanol, although storing it over time will give you some methanol as a byproduct. And that means, though, that if you're going to do it this way, you need to make sure you have the appropriate pH, you've got the right buffer salts, and osmolality. That's all on you. Doing this is potentially hazardous. I have the experience to tell you that. Changing to another name, formaldehyde is technically a gas, and its maximum concentration in water is 37%. So if you've seen those really like gallon size or 4-liter brown glass bottles, that includes small amounts of methanol added as a stabilizer to slow the acidification of the solution. Now, methanol is a coagulation fixative, so we want to be careful about keeping that concentration to a minimum because we're looking for good morphology that comes from cross-linking fixatives. And if you store this bulk formaldehyde long enough, you'll see a white precipitate that forms at the bottom of the bottle. It's time for that to go. And I have seen this in labs, and they were still using it and wondering why they got terrible fixation. Formalin, sometimes called neutral buffered formalin, is technically a 10% solution of the bulk formaldehyde from the brown glass bottle, which effectively makes that around a 3.7 formaldehyde solution. And the buffer is there to keep it to a neutral pH. Now, I looked up some of the 10% neutral buffered formalin a few years ago just to see what they assayed the concentration at, and Theirs were typically 4 to 5%, sometimes as high as 6, with a pH range right around normal, and they will acknowledge that the solution contains methanol, sometimes pretty small, but it still has methanol. And the amounts can change slightly between lots. Often they're using some form of a phosphate buffer. Our suggestion is if you're going to use these pre-made neutral buffered formalins, that you stick with a particular vendor so that you have the same buffer. They are going to try and be consistent between lot numbers. And because things can acidify over time and increase their methanol concentrations, it's just the chemistry of it's sitting there. We recommend you buy smaller amounts and not store the bottle overly long and keep it in the fridge. So maybe no more than about 6 months. So if you're buying a pint or a half-liter bottle, about 6 months. What we really encourage for labs that are perhaps infrequent users of formaldehyde, or you want to be absolutely certain that you have as little methanol in there as possible, is to use these sealed ampules of methanol-free 16% formaldehyde. The ampules store very well for a long time. The brown glass reduces photooxidation. Well, there is no oxygen in there because they're under nitrogen, actually. And we do have a protocol for making that up using PBS. Now, if you're doing perfusion and you need a lot of formaldehyde, this might be a little too expensive and time-consuming to go this route. Formaldehyde fixatives are reported in the literature to penetrate tissue at a rate of about 0.5 millimeter an hour at room temperature. The tissue being fixed shouldn't be more than a few millimeters in thickness, and I use a US quarter as an example, as something just in case you don't think in metric, that a US quarter, basically the thickness of 2 quarters is the most that you want it in at least one of the 3 dimensions of the sample. So it can be a wide piece of tissue, but very thin in depth. Larger pieces of tissue, the outside edges can end up being overfixed, and then the inside parts are underfixed. And that can allow for misinterpretation of your staining results, either using regular colored histologic stains or if you're doing immunostaining. If those epitopes have been autolyzed, then they may no longer stain, and you could misinterpret things. You want to do your fixation time and your temperatures and be consistent with them, because temperature affects penetration rate. You don't really want to overfix. Overfixation can lead to autofluorescence and also make it difficult to do your staining, your immunostaining. As an example, just to think in 3 dimensions here, you've got a large cube of tissue, and if we consider the effective penetration rate, you can see that within about an hour that slice is doing very well, but that it takes a while for the fixative to completely penetrate to the center of this very chunky cube on the left here. Very thin samples like cells on a cover slip, can actually require fairly short fixation time and may even require a lower concentration of formaldehyde. You don't want to overfix. You want to fix appropriately, but not overfix. For a cultured cell, 15 to 30 minutes might be sufficient, but you should test and standardize your protocols, because you don't want to make your immunostaining difficult. And the volume of fixative should be at least 20 times the volume of the tissue. And if for some reason, because you're putting pieces of an organ in there, the solution becomes bloody, definitely replace the soiled fixative after an hour. That's highly recommended. People working with plant tissues and invertebrates will find that it's difficult to get chemical fixatives into the tissues, and you can end up with poor fixation. There are some microwave techniques with chemical fixatives. You want to be really careful, because now you are heating up a known carcinogen. So you want to do this in a hood, better yet with a scientific grade microwave that also has a venting system. Or high pressure freezing can also improve the morphology of these samples. And again, here are our image sources for this one.